But we are genuinely going to talk about something today, or start talking about something today, which is still not understood. And it's going to be confusing for you, and that's good, because it's confusing for me. It's hard, okay? And I'm going to do my best to shepherd you through these troubled waters.
What you're saying is ask as many questions as possible.
Yeah, you can ask as many questions as possible. Now, the flavor of what we're going to do today, you can't start asking questions. There's nothing to ask questions about yet. The flavor of what we're going to do today is going to be familiar to some of you if you've taken quantum mechanics, advanced quantum mechanics, and for those of you who haven't, you should see something like this in due time. You might not have seen it in the abstract way that we're going to talk about it, but hopefully this will shed some insight into the presentation when you see it in quantum. But it's going to be critical for us because we're going to take everything that we do today, and then when we meet in class on Tuesday, we're going to do it relativistically. We're going to do it in 4 dimensions, and it's going to completely change the result, okay? So today it'll be abstract and confusing, but it might be a little familiar, but I promise you on Tuesday, shit's going to get real, okay? So with regards to the schedule, now that we had a snow day and everything got thrown off, I am tempted to just, for now at least, maintain having the quizzes on Thursday unless I hear some significant groans. And part of that is because we are going to have President's Day weekend where we're not going to have Monday office hours, and so having a quiz on Thursday of that week would be far better than having it on Tuesday of that week. So for now, we're probably just going to keep the 2-lecture sort of structure for each homework assignment. So your next one will be due next Thursday, and we'll have a quiz next Thursday. Okay? And then lastly, with regards to my Monday office hours, I really need to make some meetings between 3 and 4. So I'm thinking about having my office hours from 2 to 3 and then 4 to 6. Is there anyone for whom they're just screwed because they can only make the 3 to 4? And you suck. I don't know. What am I supposed to do with that? But Wednesday, can you come on Wednesday? 2 to 4? Man, killing me. Killing me. Okay, well I might have to pull a class electronically or something and figure this out, because I need to make these meetings. They got scheduled after I set my office hours. But anyway, okay, well I'll have to adjust that later. Okay, so here we go. So I'm going to start sort of a little philosophically. So in physics and in math, a lot of times our first pass at a definition of things is in terms of something really concrete, something that's not abstract, something we can really wrap our hands around in a sense. So to give you an example, I might say this thing, cosine of theta, and that might have some sort of, you can't just do it in your head, like you can multiply and add numbers in your head, But fortunately, there's a very concrete definition of this, right? The definition of this is, if I construct a right triangle, one of its interior angles being the angle theta, then if I get a meter stick and I measure that guy, and I measure this guy, the hypotenuse and the adjacent sides of that right triangle, then this is exactly the length of the adjacent side over the hypotenuse of the triangle, okay? So you can take that as a definition of cosine of theta, and it is in terms of something very concrete, right? And in fact, it gives you a way to evaluate cosine theta even if you don't have a calculator, provided you have a triangle and a meter stick, okay? But, and this is a theme today, sometimes we actually get a lot of mileage out of having a more abstract definition of things. So if we allow ourselves to define cosine of theta in a more abstract way, that's not necessarily directly connected to something concrete that you can put your hands on, you can, in some cases, make some very deep connections to other things, which you might not have been expecting. So for example, if instead of defining cosine theta in terms of right triangle trigonometry, I allow myself to define cosine theta. Well, actually, let me ask you this question. To motivate an abstract definition. So maybe we should motivate our abstract definitions before we just launch into them. So cosine of theta defined this way makes sense, concrete, everything, right? Okay. Now if I took this definition and I said, okay, fine, what's that? The procedure is obvious, right? You go and you build a right triangle with an interior angle that is imaginary. I got one of those right here. I'm just kidding. You can't do that. Applying this definition to this argument doesn't work, all right? So this is kind of a bust. However, if we allow ourselves to utilize as our definition of cosine theta its Taylor expansion, and this Taylor expansion might be useful to write down and we'll come back later. Okay. Then, not only are we free to use this to evaluate the cosine when the angle is some real angle theta, but it makes just as much sense if we insert an imaginary angle. Because after all, squaring and cubing and quadratizing imaginary numbers is, you know how to do that. Okay. Of course, in all of this, in case you forgot, I is the square root of -1. Okay? Now, beyond that, okay, yeah, so now you can take the cosine of an imaginary number. But in addition to this, you now get to find connections. So for example, many of you are probably aware that cosh of theta, which we define as the sum of e to the theta plus e to the minus theta, which has no resemblance to a triangle whatsoever, right? Actually ends up being exactly the cosine of I theta. A relationship that you would never think of if you just looked at this definition and then said, I wonder how that's related to this. Well, I don't know. Okay? But through the Taylor expansion, using that as the definition of cosine theta, you can generalize it to imaginary angles, and you can find some interesting relationships. Okay? Things which were equivalent, which you never would have guessed. That's what we're going to do today. We're going to start with something very concrete, and by looking at it in more abstract ways, we're eventually going to be able to connect it to something which is very, very not concrete, but which turns out to be incredibly important for physics. Okay? So, what is the thing that we're going to start with? Well, when we do physics, we like to think of physics as sort of predicated on the assumption that there's geometry, that we move around and, you know, that there's a distance between my fist and Robin's face right now, and we can make that distance smaller, larger, and, you know, so there's a lot of concrete, geometric, like bedrock to a lot of our starting points in physics. And one of the most important bedrocks is the idea that if we have a geometry, we have a space, then we can coordinatize it, okay? So coordinates, whenever we work with coordinates, whenever we talk about changing coordinates or expressing something in a certain coordinate system, that is a very geometric way of working with things, okay? And of course, as you are hopefully now very familiar, when you talk about transformations, transformations of coordinates have played a very important role in us setting up how to think about at least representations of the rotation group, because if we know how coordinates transform, okay, we kind of use the transformation of coordinates to define this thing lambda, we can also generalize that to say, well, this is really just a vector. You know, it's got components like this. So I can take this as the rule for how any vector transforms. So we start with something very concrete, the coordinates, and then we just adapt that definition to vectors in general, and then we can talk about dual vectors and tensors and so forth. Okay? So this starting point, this concrete starting point leads us to the idea of scalars. The lengths of vectors is a scalar. It leads us to vectors, dual vectors, and tensors in general. Of course, scalars and vectors and dual vectors are themselves tensors. They're the only ones that get special names. Okay? But we might wonder, is there more? Is there more interesting things out there than just this set of stuff? And it turns out that there is, and it's crucially important for what we're doing in this class. But to discover it, we have to get ourselves away from this geometric starting point. And to get ourselves away from this geometric starting point, we've got to sort of abstract the way we think about this stuff. Okay? In the process of abstracting, we're actually going to get something that's useful. And this is going to be a method. So this is the motivation. We're going to be looking for something beyond just this set of quantities that we've dealt with before. We want to see if there's anything else. And in the process of formalizing our way of handling things, we're actually going to develop a new tool, and that is we're going to develop a way to compare continuous groups. So remember, if you want to compare discrete groups, so if I hand you a finite discrete group, or two finite discrete groups, and I say, are they equal? Are they the same? How do you determine if they're the same or not?
Multiplication table.
You compare their multiplication tables, exactly. So the simplest possible example is if I take even and odd, then you can fill this out, and Daniel will be happy to help me do this. Daniel, what goes here?
Even. Odd. Or even.
Even, yes. Odd times odd is even. Okay? However, if I take multiplication by plus and minus 1, notice that's not odd and even. Those are both odd numbers. But if I take multiplication by plus and minus 1, then Will is not here. Claudia is going to help me fill this one out.
1, negative 1, negative 1, 1.
Good. And you'll notice these multiplication tables are essentially the same. And in fact, these two groups are the same. Yes?
I think you mean even plus even, or even plus odd, because 3 times 3 is 9, which is odd.
Oh yeah, you're right. Addition. Yeah, addition. Right. So yeah, we call it a multiplication table, and my brain automatically goes to multiplication. But you're right. If we add, and if we add even and even here. Okay, good. Thanks, man. Okay,
So when you make a multiplication table like this, do you have to define which operator you're talking about?
Sure, yeah. The group has to be well defined, and you're right. I should have been more precise in the definition of the group, and if I had actually been more precise, I might have actually called it a mistake. So here we have in mind addition with even integers or addition with odd integers.
Okay. You would make that distinction before.
Yeah. And there's a lot of different ways of defining this exact same group. Okay. Now, I did specify a finite discrete group because if we happen to have an infinite discrete group, we're going to get really tired constructing the multiplication table, right? Because there's how many elements in the multiplication table of an infinite discrete group? Yes.
Can you compare finite and infinite discrete groups together?
How could they possibly be the same? One multiplication table would be finite, and one multiplication table would be infinite.
So
they definitely can't be the same.
When we're saying these two tables are equal, are we just saying that it's...
We're essentially observing the same structure. That the element here, if it corresponds to the element here, so too does the element here correspond to the element here.
Couldn't you say that about, like, if you had a 3 by 3, then as long as...
So the number of elements of the groups have to be the same. I mean, I'll just throw that at you. Therefore, the dimension of the multiplication tables has to be the same. Yes, very easy.
So the group negative 1 and 1 is finite, and the group evens and odds is infinite.
So that's a good observation. So again, it's the way that we define the group. So I'm going to take my group to be two elements, addition of an even and addition of an odd. And any even integer would do, any odd integer would do. Okay? That's a really good observation. So we have to be really careful at defining these groups. I appreciate that. Yes?
Is there a way to like equate infinite discrete group with a continuous finite group?
No. No. But I don't want to get too hung up on discrete groups because we're not going to talk about discrete groups. We're going to talk about them later, but this is, you can sink your teeth around this, but we really need to move on to continuous groups. So for continuous groups, this is clearly not going to work, right? Essentially for the same reason that you can't do it for infinite discrete groups, because the multiplication table would be infinite, okay? Even if the continuous group is compact, like the rotations, there's an infinite number of rotations, okay, because it's continuous. So comparing multiplication tables is not going to give us a way to compare continuous groups. So we might wonder, off the cuff, is there anything that we might think of comparing between continuous groups to ask whether they're the same? So, yeah. Their range of values. So whether it's compact or non-compact?
Sure.
Yeah, good. So there's some properties of groups we can compare. So if two groups are compact, well, actually, what we can do is we can nullify the comparison by saying if one group is compact and the other group is non-compact, they can't be the same. Okay, and that turns out to be a useful comparison. Okay, although that can, in some situations when things are complicated, it can disguise itself, and we'll see an example of that in due time. What else might we compare?
Maybe if you could come up with a mapping that's one-to-one onto.
Sure, if you can construct an isomorphism explicitly, then. But I'm just talking about just generically looking at features of two different groups. Constructing the map is essentially proving their equivalence. So.
You like look at one or not?
Sure, yeah. If one group is abelian and another group is not abelian, then there's no way they can be the same. Okay. There's another really important one to compare. Yeah, Robin.
You compare subgroups.
So basically, what do you mean by compare subgroups?
So if you,
let me say SO3 has a subgroup SO2, SO4 has a subgroup SO2, but SO3 is not equal to SO4. So does that make sense?
yeah.
So when you say compare subgroups, I'm not. So you can be technical and talk about their complete decomposition into an irreducible set of subgroups, but that's a slightly more sophisticated thing than we've covered. Okay. There's another really important thing that we've talked about. We actually spent some time calculating it. That's going to be very important for continuous groups, and it's actually the way that we organize our thoughts of continuous groups. Not exactly. Not exactly. That's a really good guess, though. Yeah.
The number of free parameters.
Yes, good. The number of free parameters. This is actually one of the more important things to think about, because if I can describe all the elements of one group with one free parameter, but for another group it takes 3, then there's 3 different directions that I can transform in this group, but there's only one direction I can transform in this one. So it's going to have a lot richer structure the more free parameters I have. So if two groups are going to be equal, they have to have the same number of free parameters. All right? Yes?
But what if one group doesn't represent the physics faithfully and the other group?
So we're not talking about faithfulness of representations. We're genuinely just talking about groups. Yeah, groups. Now, on the note of representations, could we compare the dimensionality of matrices? Can we say if one group is represented by 2x2 matrices and another group is represented by 3x3 matrices, they can't possibly be the same? No.
The same group with the matrices.
Yeah, and this you learned from your homework. You can represent the same group with matrices of different dimensions. Okay? You can do that with one group. So saying that one group has 3 by 3, and one group has 5 by 5 doesn't necessarily mean they're different groups, okay? So this is no good. What about real versus complex? If one group is represented by real matrices and another group is represented by complex matrices, does that mean they can't be the same? No, and again, you saw that in your homework, your first homework. Okay, man, that was a good homework. You guys learned a lot. Okay, so what we want to do is we want to formalize a way to compare groups. We want to sort of find an abstract way of saying, yeah, these two groups are the same or they're not. And in doing so, we're going to come back to that first point, which was discovering new objects that are important in physics beyond the stuff we've already encountered. Yes?
So obviously, if we find that one of these is not true, we show that they aren't the same. But to show that they're all true, actually,
Yeah, no, they're not sufficient. They're necessary, but not sufficient. And yeah. So I haven't given you, I mean, I'm going to give you a better algorithm for comparing things. These are just some of the observations that we can make, and some of them will be important. We will find equivalences between groups of different, represented by matrices of different dimensions. We will find equivalences between groups represented by real and complex matrices, but we're always going to have the same number of free parameters, and we're always going to have to be either abelian or not abelian, and compact versus non-compact. Okay? So, so how are we going to go about talking about these infinite groups? You know, continuous groups are infinite. They have an infinite number of things. It's kind of hard to wrap your head around. Well, fortunately, the groups that we most often work with, and in fact, the groups that we're going to be working with in the standard model, form what are called Lie groups. Okay? And there are a whole host of Lie groups. Fortunately, every group that we're going to talk about in this course essentially forms a Lie group. So the group of space-time transformations, SO1, 3, the group associated with strong interactions, the weak interactions, electromagnetism, and even, and in most of today we'll talk about spatial rotations, even spatial rotations. These are all examples of Lie groups. Now, an informal way of thinking about Lie groups is as follows. A Lie group, well, technically, the technical definition, a Lie group itself forms a differentiable manifold. And all of these words carry a lot of significance, particularly the word manifold. If you've ever encountered it, it's a very specifically designed or defined thing. Okay, locally it's always Rn. Okay, but what's important, the sort of heuristic way, or the heuristic appreciation of this statement is Lie groups as a smooth manifold. So it's like a space, allow us through their differentiable structure to, if we understand what's going on over an infinitesimal displacement in a point in this manifold, then we can extrapolate what's happening over larger displacements. Okay? But of course, critical in this and working with these is understanding how many distinct infinitesimal displacements there are. So for example, if I think about translations in 3 dimensions, you know, you can move in the z direction, you can move in the x direction, you can move in the y direction, or you can move in any combination. Okay? There are an infinite number of directions you can translate, but somehow there's something special about 3. There are 3 sort of defining translations, and any other translation can be read as a linear combination of those 3. Okay? So this counting is exactly the counting of the free parameters that we've been doing. So knowing the number of free parameters in a group is telling you about the dimension of this space. All right? Now, this idea about if you know what to do over a very small distance, you can build up what to do over larger distances is already something that you're very familiar with. So for example, if I gave you the matrix that rotates by 1 degree in the YZ plane. So remember, this is a rotation around the x-axis. So if I gave you this matrix, you could take it and construct this matrix. How would you do it? Yeah, you'd operate on this 44 times, because you've already got one. So if I take RYZ 1 degree and raise it to the 45th power, okay, then I can build up large transformations as long as I know a small transformation just by compounding them, okay? Now this is sort of a discrete starting point, right? We couldn't start here and figure out how to rotate by ½ a degree. Okay, and one of the things we know about rotations is that this parameter theta is continuous. So this is sort of a simple model of how you build large things from a small thing, but what we want to do is start with something that we can build an arbitrary transformation with of any argument. Okay, so what we really need to understand is what is the transformation for an infinitesimal value of the rotation angle, delta theta. Okay, if I know what it is for an infinitesimal, then I can build up an arbitrary thing just by compounding enough of them. Now you automatically see something that's going to be a little weird. How many do you multiply together? Is it infinite? I mean, you have to take your interval and divide it into infinitesimals. So how is that going to work? It's a little weird. Okay, well that's going to be an important part of the story. Fortunately, though, the definition of Lie groups is equipped with a way to combine these infinitesimals in order to build up something which is finite. Okay. So the idea here is the groups that we're dealing with are continuous, both in order to figure out how to compare them and to discover new representations which we couldn't possibly figure out if we kept thinking concretely. We're going to explore properties that are specific to Lie groups. And it hinges on this idea that Lie groups allow you to start with a few infinitesimal transformations and with those in hand build up almost everything else. Okay? And that almost will come in due time. So now we want to go through the machinery of this. And again, this is stuff that some of you have seen before and most of you will see at some point. It might not look exactly like this, but this is not empty words. All right. So if we have a Lie group, a general element of a Lie group can be written, and what I mean by general is for an arbitrary transformation parameter. It doesn't have to be infinitesimal. It can be written using what we call the exponential map. So if A is the element of the Lie group, I can express A as the exponential of I, G, A, V, A. Okay? Where GA generates the transformation and VA parameterizes it. Okay, so let me tell you what these words mean. Generates the transformation essentially means it tells you which transformation you're doing. So to go to a familiar example, if I talk about SO3, then we know that essentially this includes rotations around the x-axis, rotations around the y-axis, and rotations around the z-axis. God, I can never do this. That's why. There we go. So the generators tell you, okay, you're going to do this one, or you're going to do this one, or you're going to do this one, or maybe you're going to do a little bit of each. Okay? And then The VA parameterizes the actual transformation you're going to do. So it would correspond to the angles. Okay, if I say I'm going to do a rotation around the x-axis, I haven't told you what I'm doing yet, right? Because I got to say I'm doing a rotation around the x-axis by this angle. So the generators tell you what transformation you're doing, and the VAs are going to parameterize the transformation. So we call them the parameters of the transformation. Yes?
Just to know, are these A's like just denoting like what they are, or are we actually using that as summation?
So let me tell you what that. So a couple of notes. So I'll get to yours in the second bullet point, but the first bullet point is if A is an n by n matrix, okay, if the transformation we're working with is an n by n matrix, then so is the generator. Okay? So we are exponentiating matrices. We'll learn how to work with that in a minute. Okay? The second point is the combination GA-VA allows us to do a transformation that is a combination of several different types of transformations. So the way that you can think about this is an arbitrary rotation would be some rotation around the x-axis with some parameter, maybe call it theta, and then some transformation around the z or around the y-axis with some other angle phi, and then some rotation around the z-axis with an angle psi. Okay, so the VA you can think of like a vector of parameters. So if I'm doing rotations in 3 dimensions, it's a vector whose elements are angles. Each angle gets paired up with a particular axis of rotation. Okay? I could take this expression and I could do a single rotation around one axis, in which case my vector would be theta 0, 0. And that would correspond to a rotation only about the x-axis. Or I could do a rotation simultaneously around all of the axes. And that would be a more complicated combination of rotations. Okay? But remember, if I take several different rotations and I combine them, the net result has to be a rotation. That's the definition of a group. It might be a weird thing in the end, but if I do 3 independent rotations around x, y, and z, the net is just a rotation. Okay? Okay, so now what I'm going to do is I'm just going to make this very concrete. I'm actually going to show you this exponential map for an example that you're probably familiar with. And in the process of this, what we're going to be able to do is, at least for the case in question, we're going to be able to extract what these generators are. So, for the course of today, we're going to stick to spatial rotations, which thus far we have best identified with SO3. Okay? Of course, you can have scalars, in which case you don't have to say SO3, you can just say the identity, because everything acts like the identity on the scalar. All right? But for today, we're going to stick with just spatial rotations, and then next time we're going to extend all of this to 4 dimensions and include Lorentz transformations. Okay, so as an example, I'm just going to look at a rotation around the x-axis. And remember, if you're confused about this, I don't want to call this Rx, because if we go to higher dimensions, which we will next time, saying a rotation around the x-axis doesn't mean anything, because there's 3 directions perpendicular to x. So you have to really specify it by the plane you're rotating in. So if I rotate in the yz plane, then this would be e to the I, the generator of a rotation in the yz plane, times whatever angle I'm going to rotate by. And now we immediately have an interesting problem. This, as it acts on vectors, looks like what? Yeah, it's a matrix. It's a 3 by 3 matrix. This is the exponential of a matrix. Now it is a matrix times a number. All right, so if you want, what we're doing in this example is we're taking our VA, the vector of parameters, and we're saying theta 0, 0. So only when you take the generators and pair them up, the only one that survives is the first one. Okay? But still, this is a matrix, and because this is a matrix. So we have the exponential of a matrix. How do you exponentiate a matrix? Say again? With a Taylor series. Okay, you use a Taylor series. So if we expand out this with the Taylor series for a complex exponential, we're going to have I plus I. Oh, damn, I missed it. All right, Coach, so pretend we didn't answer that question. And then I go, this is the exponential of a matrix. I have to do this because I put it in my notes, and if I don't put it in my notes. And then the question is, what's that, Flournoy? I'm not going to do it again this time. Okay, so we define this, the exponential of a matrix, to its Taylor series. So let's write down the Taylor series expansion here. And I will go to third order just for purposes of comparison. Okay. And, okay, so at the end of the day, this is a form of the rotation operator that we know from our physical intuitive sense of, oh, this is what you would do to the coordinates if you did a rotation. This is an abstract definition. But let's pair them up and let's say this thing has to be the same as this. Okay? Now, in order to sort of extricate what is really essential in identifying these two, remember we're looking for a definition that's working around infinitesimal angles, small angles. So why don't we take this expression and expand each and every term for a small angle? Okay? And this is going to give us a way to make this comparison. So if I do the expansion, of course these terms don't do anything. And then cosine leading order is going to be 1 minus 1 over 2 factorial theta squared, plus other terms, and then the sine. And then with the opposite sign here, and then same sign here. Okay, so there is my rotation matrix expanded for small angles. And what's nice about doing that, actually it's an arbitrary angle, to be honest with you, but what's nice about looking at the expansion here is I now have an infinite sum representing my rotation matrix that I can compare with the infinite sum here. And comparing two infinite sums is a little bit easier than comparing an infinite sum to a finite expression. Okay? Yes?
So how did you end up from VA as a vector going into the exponent as just theta? Like I understand that the other two entries are 0 for this case, but it's still not a scalar. Like it has different dimensionality. Well, why did it go to a
okay, yeah, that's a good question. So GA is a vector of matrices. Okay, it's a dual vector of matrices, if you will, but it's a thing which has a matrix in each row, or yeah, in each column.
The
Sorry.
other two.
Yeah. VA, however, is just a vector of numbers. So you're pairing up a number with each matrix. Here I'm literally just using the vector idea to just pair things up. There's no metric in this or anything weird. It's not a spatial vector. It's just a way of pairing things up. Okay, so what I'm going to argue to you, I'm not going to prove it, because I'm going to let you prove it to yourself in your homework, is that, and it's not hard, it's actually really straightforward, there's nothing weird about it, is that if you compare this to this, what you will discover is that if I identify GRYZ with the following matrix, okay, those are I's. Okay, so it's mostly zeros. It's got two non-zero entries, a minus I and an I. But if I say that GRYZ is given by that matrix, then this expression becomes exactly this expression. Okay? And you might say to yourself, how in God's name are you going to show that? Well, there's a really nice property of this that you can make use of, and that's if you square it, it's just the identity. Sorry, it's not the identity. It is, but it isn't. It's the identity in the lower two blocks where things are happening. Which you don't, I mean, you don't have to take my word for that. You can multiply it out and see it. Okay? But the nice thing about that is, if that's the identity in the lower two blocks, what is this? Sorry, this is YZ. What's this? Yeah, it's the first one. So you can evaluate this to an arbitrary power, just based on whether you're raising it to an even or odd power. Okay? So in your homework, what I'm going to ask you to do is to take this matrix, all right, and basically plug it into this expression. And using these results, you should see, remember, this is going to be a 3 by 3 matrix. It's going to be an infinite number of them added together. But if you compare it a term at a time, you'll see exactly this matrix appear. Okay? Now, similarly, you could play the same game for rotations in the ZX plane and rotations in the XY plane, and you'll get different expressions for the generators. And in the ZX plane, you're going to get 0, 0, minus I, 0, 0, I, 0, 0. And in the XY plane, 0, I, minus I, 0, 0, 0, 0, 0, 0. Okay? And again, you can get that by writing down this rotation matrix for a rotation in the ZX plane. So all you would do is move the cosine and sine in different locations and then play the whole game again. You want me to make you do all three of them for your homework?
Sure.
Yeah, no, we'll just do one. Okay, yes?
I guess I'm confused. So you're getting those by plugging those into there?
No. So this is an inspired guess.
So how
But
would
you
we-
can verify that this is correct by taking this matrix and plugging it in here. And so
Are we gonna find out how to be inspired guessers?
no, don't worry about that. Don't worry about that. This is not that's not an interesting problem to solve. Like you could figure it out with trial and error. But I'm not interested in making you expert guessers of generators of groups. It's not. If you get into it deep enough, eventually you can prove to yourself rather quickly that these matrices have to be antisymmetric, that they have to have mostly zeros at most two non-zero entries. There's lots of properties that you can derive, but the truth is, and this is interesting, this is not the only set of three matrices that you could use. There's actually other solutions. Okay? They come in pairs of three. And the solutions are actually related to each other by, surprise, surprise, a rotation. Okay? This is all predicated on thinking about some coordinate system, and you're defining the rotations as rotation in this plane, rotation in this plane. If I choose a different coordinate system, I can talk about my rotations in the planes of the new axes, which in the old axes are weird transformations. Okay? Yes?
So if you can't define the transformation as a matrix, like we did with the cosines and sines,
Then this doesn't work. Okay? Fortunately, for most of the league, all the league groups we're going to work with this, in this class, you can represent them by matrices. But there are exceptions. Some of them are actually called exceptional groups. But we don't want to get into exceptional groups. That's the weirdest thing I've ever encountered in all of my studies in physics. Okay? So you can't possibly sit here and go through the details of this by the end of class, but do you understand the methodology? Take this matrix, plug it in. All you're doing is powers of it, which that little rule I gave you is going to make that easy. And you should be able to, term by term, figure out, oh, that looks like that. Okay? All right. By the way, for those of you who are interested, I said that the Lie groups form a manifold. The generators actually correspond to a basis in the tangent space of that manifold at the identity, at the origin. And that's not going to mean very much to most of you, but for those who took general relativity, they know some of those words. Okay, so well, it's interesting because in general relativity, you learn to think very abstractly about spaces and what spaces mean and so forth. And when you suddenly realize that these groups that we're working with form spaces, and then you get to carry over a lot of power of these.
Is there an easy way using these groups to find the metric of that space? Is that like an easy?
Well, yeah. Remember the groups. The groups are defined like so. So if I gave you the set of groups and their properties, you could probably extricate the properties of the metric from that. But whether that's easy or not is a different thing. Okay, so now here's the important part. Everything that I've done so far has been concrete, right? It's been abstract at all. It's been very concrete. No, it's been concrete because everything so far is based ultimately on coordinates. And coordinates are, in physics, a very concrete way of thinking about space and transformations in space. Okay? The fact that we wrote down 3x3 matrices is a reflection of the fact that we started by thinking of coordinates, because there are 3 coordinates. Okay? The form of those matrices was motivated by the form of a rotation matrix as it acts on coordinates. I would like to get away from that. So in order to get away from it, what we have to do is we have to take the information we discovered and somehow extricate the juiciest details without referencing coordinates. And to do that, we're going to introduce what is called the Lie algebra of the generators. The Lie algebra of the generators of the rotation group looks like the following. If I take, for example, the generator for rotations in the YZ plane, and I form the commutator with the rotation generator for rotations in the ZX plane. Okay, so remember the commutator is defined as doing it one way minus doing it the other way. And this is the definition of the commutator. I'm glad you put your hand down, Matt. Then what you will discover is if you take those matrices right there and you do this, again, you can't do this right now, but you can do it in your own time, and you will. If you do this, you will find that the result is just minus I times that guy. So if you take the commutator of 2 generators, you basically get back a number times one of the other generators. And in fact, for Lie algebras in general, they will always exhibit a structure like this. If you take the commutator of generators, you'll get back a linear combination of the other generators. Doesn't necessarily have to be one of them. Yes?
Isn't that kind of falling through because we talked about a group and we defined a group such that if you took and did the transformations, you would get another transformation in the group?
So the fact that you combine two transformations and get a transformation is certainly reflected in here, but it's not identically the same thing. For example, this is not a transformation. This is a generator. How do you get the transformation like this? Okay. Moreover, this is not just two transformations combined. It's two transformations combined in a very specific way. Okay, but it is tied in with that. It's just not identical to it. Yeah.
Is a Lie algebra always a commutator?
The Lie algebras are always defined with the commutator. Okay, and we'll talk about the other algebras in a minute if we get to it. Okay. So what I'm going to do now is, this is getting really cumbersome. So I'm going to call RYZ, I'm just going to call that 1. I'm going to call RZX 2, and I'm going to call RXY 3. Okay, 1, 2, 3. Then I can write the algebra for rotations in general. The GJ is minus I epsilon ijk gk. Okay? So let me explain to you what this expression means. First of all, k here is summed over. Now all of these I, j, k can be any of 1, 2, 3. Okay? So I sum over this. So I take the right-hand side and I write it with the I and j I pick here, and then I do 1, and then I do it with 2, and I do it with 3, and I add those together. Okay? This is the completely anti-symmetric Levi-Civita symbol. So what that means is epsilon ijk is epsilon, and then if you do even permutations of this, so jki, epsilon kij, those are all equal to plus 1. Any anti-symmetric combination, is equal to minus 1, and if I repeat an index anywhere, it's equal to 0. Okay, so the numerical values of this are either plus 1 if you have things in a cyclic ordering. So for example, if I have 1, 2, 3, or 2, 3, 1, or 3, 1, 2, it's plus 1, and if I switch two of those and then do a cyclic ordering, I get minus 1. You can literally write every single term out. Okay? If I ever repeat an index, I get 0. Okay, so let's actually see that we reproduce this using that formula. So if I say G1, comma G2, that's this and this, then I expect I should get minus epsilon 1, 2, 1, G1 minus I epsilon 1, 2, 2, G2, minus I epsilon 1, 2, 3, G3. What's this?
0.
What's this?
0.
What's this?
0.
Yeah, this is the only one that survives. And that's exactly what I should have gotten. Whereas it is. Okay? You good? Yeah.
Is it arbitrary that you chose that RYZ
Yeah, this is just a label. It's just a label. You could have called it XYZ. I like this because you sum over numbers. But you could sum over labels too.
So if we had, say, like 5 generators, the commutator of 2 of them would give us a sum of the 3 others?
It doesn't necessarily have to follow that way. In fact, exactly what appears on the right-hand side is different for different groups. They're called the structure constants of the group. This happens to have one set of structure constants, and they're just identical with the Levi-Civita. You could have a sum of 1 or 2 or all of, it just depends. It's different for different groups. Okay. So the claim is, if we have a Lie group, okay, and we have the algebra of its generators, then the algebra of its generators completely tell us about the group at least if you're doing transformations near the identity, small transformations. And you might say, what, Flournoy? How you talk like that? Well, look, if I took this equation and gave it to you, okay, with these things specified, okay, if I said, I'm not going to tell you what GI, GJ, and GK are. I'm not going to tell you. All I'm going to tell you is that they satisfy this, where this epsilon, this Levi-Civita is given by this. And I said, hey, go find some 3x3 matrices which solve this equation. One set of solutions are these. So I could give you these, or I could give you the algebra. And from the algebra, you can discover the generators. So with Lie groups, we often find that we get a lot of mileage by specifying things given the algebra instead of starting with some concrete representation like this is what it does to vectors.
So this algebra that we've got right here is only for SO3 special rotations? Or is it for any group that we talk about?
Well, unfortunately, the most interesting part of the lecture comes in the last 30 seconds of class. So, we are going to have to save this for next time. But what we're going to, I'll give you a preview. What we're going to find is I can take this algebra and I can find solutions for the G's that are actually 2x2 complex matrices. And you might say, okay, if I take a 2x2 complex matrix and I plug it in here, what is the A going to come out to be? A 2x2 complex matrix. So somehow the Lie algebra of rotations can be represented by 2x2 complex matrices acting on something. That's clearly not a vector in space-time, because a vector in space-time, or a vector in space, sorry, has 3 components. It's not a scalar. It's not even a tensor. What is it? And we're going to discover next time what that is, but I'm going to leave you with a quote, which I think is very interesting. Michael Atiyah is one of the greatest mathematicians of the 20th century, and he spent his entire life working on this particular kind of object. And at the end of the day, this is what he had to say about it. Atiyah is credited with working pretty much his entire mathematical career on spinors, and at the end of the day saying, I do not understand what spinors are. Okay? And so next time we're going to start discovering spinors, beginning with spatial rotation spinors, and then hopefully very quickly moving into relativistic spinors, where things will look significantly different. Yes.
So,
Yes.
so if two groups have the same algebra they have like the same
Not necessarily. We're going to talk about that next time. So they are the same as they're within the identity for small transformations, but if you look at big transformations, they're not the No, yeah. So in quantum mechanics, you would